video, I want to walk through an example problem showing an oblique impact. So in this problem we have two balls of equal mass which are coming into contact. The ball on the left is traveling at 30 feet per second at an orientation of 30 degrees or with a direction of 30 degrees off of the normal axis direction. And the second ball on the right is traveling with 40 feet per second velocity at an orientation of 60 degrees off the normal. And then we're given that there is a coefficient of restitution between the two of 0.9. So my first step is to start calculating some things that I know. And we're going to call or label the ball on the left A and the ball on the right B, and then use that to write the velocities that we know. So I'm going to break the velocity components into their normal and tangential components, and these are all velocities prior to impact. So basically we're just going to use trigonometry in order to evaluate these. So the first ball is traveling at 30 feet per second, and if I want the normal component I can take the cosine of the angle and I get 26. And I can carry this out for each component that I'm trying to calculate. Adding on this normal component for B, it's in the negative direction, so making sure I tag that little negative sign out there. So far we're just doing some simple math working through these two things. Now the next bit of information that we need to recall in this case is that the restitution, the coefficient of restitution, only really affects normal direction of travel. So therefore we're going to retain our velocity in the tangential direction, which means I can write the velocity of each component in the tangential direction after impact to be equal to the tangential velocity before the impact. Now I've got a bunch of things here figured out, and my only remaining component is to write my conservation of momentum equation. So conservation of momentum affects all of the, or makes use of all of the normal direction velocities before and after the impact. Now notice that all of my m variables here for mass, I've left them just as m, and I didn't have to label those with subscripts using A or B because we specified that the mass of the two balls was going to be the same. What that also does for us then is allows us to cross off each of these masses because we could divide that out of the equation. And we can go ahead and substitute in our known values for the pre-collision situation. First, for particle A we had 26, and for particle B we had negative 20. And what this leaves us with is an equation that includes the normal direction after collision of each particle. All right. The last bit that we need to use to make use of is this coefficient of restitution. So I'm going to take my equation that I had developed in the prior video and write in my remaining terms. And this gives me VBN2 minus VAN2 equals 41.4. All right. So between all of these things, I should have enough information in order to solve my equations. Now you'll note that pretty much everything on the top here is all just solved, right? Those numbers we've figured out. And what I'm left with is in the bottom half of my work here is two equations. And each of these have the same two unknowns, so that's a two equation, two unknown system. So I can go ahead and solve. And what I get is 17.7 feet per second. Now I've left off the negative sign that would come out of this because I'm just going to show with an arrow that it's traveling to the left-hand direction. And particle B traveling to the right. So these are the two unknowns that I wasn't able to solve for more directly above, and I've used our equations to arrive at those. And I could put this back together with the tangential components up here of 15 and 34.6, and then I could get a sense of what direction I could get, direction and magnitude for that velocity vector. But for our purposes here, I'm just going to leave it broken down into tangential and normal components, understanding that that represents the full picture of the velocity of these two balls after they've made contact and where they're headed. All right, thank you.